As I was saying in the last couple of videos, we can actually use exponent laws to simplify, solve, and deal with a lot of different radicals. Sometimes it makes these problems a lot easier. But for example, say we wanted to multiply two exponential expressions with the same base. Well, the rule of thumb would be if I have, kind of returning back to a simpler case. And if you're ever a little bit stuck on, well, how would I do this math? I always recommend trying to simplify it and think about, well, what if I just had something simple? What if I had x squared times x to the fifth power? What would happen? Well, remember that if I'm multiplying exponential equations with the same base, what happens is we'd add the exponents, and that would become x to the seventh by common logic. And those same rules, and sorry, that's supposed to be a 5. It looks like kind of like a 3. But basically, all the rules of exponents we covered in chapter 4, they all still work for fractions because they work for all numbers. So basically, with roots, if we treat them as fractions, we can then just do fraction math in order to work upon them. So like in this particular case, this would be this cube root of 16 squared multiplied by the sixth root of 16 to the fifth, which would be a really, really horrible thing to try to figure out. But if we just use the rules for fractions, basically, I would need to add these fractions in order to combine them together. So I would result in 16 to the 2/3 plus 5/6 power. And then in order to add those, since those are fractions, I would need a common denominator, which between 2/3 and 5/6 is 6. So this would be 4/6 plus 5/6. 4/6 plus 5/6 is 9/6. So I'd be left with 16 to the 9/6 power. And of course, that fraction would reduce by a common factor of 3. So this would result in 16 to the 3/2 power. And then after simplifying, I could then see if, well, maybe I could figure this out as a radical, because the 3/2 power is equal to the square root of 16 cubed. And the square root of 16 is just 4. So this would be 4 cubed, which is, of course, 4 times 4, 16 times 4 is 64. So it turns out that all those horrible expressions just simplify down to 64. Of course, you could do it with the calculator, but sometimes, the calculator would not simplify it to the degree that you would need for a particular homework problem. But let's just check ourselves, make sure it's getting what we got. That's kind of the idea. Or, say we were dividing and again, remember the base must be the same in order to use those rules for exponents. But say we're dividing two exponential expressions with the same base, that would be a subtractive effect, right? I would do this one minus this one. So this would be equal to 8 to the negative 4/3 because there's a common denominator. And then that would be the cube root 1 divided by the cube root of 8 to the 4th power. And that's actually just 1/16. So again, sometimes you can figure these sorts of things out without a calculator. Or if we have a stacked series of exponents, those would multiply together. So this would result in, sorry, I'm kind of running out of space here. This would result in 36 to the 10 over 20 power, which is just equal to 36 to the 1/2, or the square root of 36, which is 6. And then, say we had particular situations where we're trying to solve what happens if I have a square root times another root, or a root of multiple things, or things such as this, where it says simplify. A lot of times changing them into their exponential form can be helpful. Like in this first case, the square root of x is equal to x to the 1/2 power. And then the square root of x cubed is equal to x to the 3/2 power. So I could kind of change them into their fractional form. Now that they're in their fractional form, I can apply the rules of exponents, which means that these would add together. So this would give me x to the 4/2 power, which is, of course, x squared. And also, technically, since it's a square root, it should be an absolute value, but since it ends up being square, it will be positive anyways, so I don't actually need the absolute value. But as I said in the last video or 2 videos ago, sometimes you got to be careful to note absolute values. And often a homework problem would have another saying here, which would say that assume all variables are positive. And basically, when it says that, if you're like, "What? Why do they say that?" Basically, it just means don't worry about the negative case, because the negative case can cause issues, as I said before, with squaring a negative becoming a positive. Anyways, or say we wanted to figure out, well, what is 9, the sixth root of 9 cubed? Again, if I rewrite that as a fraction, that would be 9 to the 3/6 power. And 3/6 reduced down to 1/2, so that would just be the square root of 9, which is 3. And sometimes it's vastly simpler to deal with the fractions in their fractional form. Now, if you have a series of different components, well, since this whole thing is raised to the is in the cube root, what we could do is rewrite this as the whole thing raised to the 1/3 power. And if you recall, when I have multiple different products all raised to the 1/3 power, this 1/3 would split to each of them. So this would change to 27 to the 1/3, a to the 3 times 1/3. And remember, this would actually multiply into those exponents. So 3 times 1/3 is just going to be 1. And then 9 times 1/3 is just going to be 3. So what this would leave me with is 27 to the 1/3 times a times b cubed. And 27 to the 1/3 is equal to the cube root of 27. And that's just 3. So ultimately, this makes 3ab cubed. And I can simplify something pretty horrible just by applying fractions and rules of exponents. Now, say for example, we had a series of multiple different roots all put together, and you're wondering, well, how would those combine, if at all? Rewriting them as fractions can help. Like basically the exterior, or like on the inside, I have x to the 1/2 because it's a square root, and that whole thing is being raised by 4th root, which is equal to the 1/4 power. So, basically it's a chain of roots, which is equal to a chain of exponents. And by rule, that's a multiplicative effect. So 1/2 times 1/4 makes 1/8. So what would actually result from all this is the 8th root of x. And basically the indices are multiplicative if it's, a simple situation like that. And remember that when there is no number, there's technically a 2 there, which is why it would become an 8.